Okay, everybody, my mic is on now. I think you can probably hear me from what I can hear in the room. My name is Simon Clegg, and welcome to the Marine Chemistry Speciation Model launch and tutorial from Woods Hole Oceanographic Institution, to those of you who are joining us remotely. So I'm Simon Clegg, as I say, and I'll be the main, although not the only speaker this afternoon. And the arrangements are a little bit more complicated than for an ordinary talk, so I'll take you through them. So in this room, there's me, there is Tara sitting at the back there, who is a helper for Python and MATLAB problems. There is Nate, and he is sitting there. He's a MATLAB helper, and also Jonathan there, who's going to be a Python helper as we go along. Monitoring Zoom, and in the chat we have May, who's sitting here at the front, and online to help those joining by Zoom, we have our colleague Mattis at UC Santa Cruz. He's an expert in Python and MATLAB, mainly on Linux and Apple machines. He may hand off Windows-related problems to us here. And Matt May is going to explain the Zoom arrangements through the chat online. Also, as part of the demonstration or the presentation, there will be some short demonstrations of the use of an Excel front end to prepare and run problems using the standalone models, which it's not a necessity to use that, but you may find it helpful. And also the use of the MATLAB function, David will demonstrate, and the use of the Python function, Tara will demonstrate later on. And for these two languages, it's worth remembering there are a couple of simple setup steps that are needed at the beginning. And if you haven't already realized, it really is necessary to read the instructions for those. So what we're going to do first, over about 12 slides or so, is a quick outline of how we'll spend the afternoon, summarize a few basics about the science behind the models, summarize what the models can calculate, and mention a few of the limitations that there are. It's a model, so there's always a limitation. So the most important thing for you, I think, is to aim to finish the afternoon, not necessarily understanding everything that's presented. Some people, MATLAB and or Python might not be of interest. But do try to understand how to do calculations that are useful or will be likely to be useful for your work. And if you leave being confident of that, then we've succeeded. And remember, we're all here to answer questions, so no question is too simple. So don't worry about that. First of all, just a couple of acknowledgements. Our funding comes from NSF here in the USA, NERC in the UK. The principal investigators on the project are me, Andrew Dixon at Scripps, and Heather Benway here. And although it's not relevant to the work today, we have a measurement program in support of model development led by NIST, with contributions by their equivalents in Germany and in Japan. And MarChemSpec is a product of this SCORE working group here, of which David is chair. So in this, for this session, we hope and expect that you've downloaded the models of interest to your computers and verified that you can run them. You may want to refer to the documentation, and if you like to use printed copies, as I do, there are some available on the tables. Otherwise, you should use the PDFs that were provided in the downloads. So in this presentation, this first part, I'll give a quick summary of the science basics and the ways of using the models. Then at the end of this little section, we'll have a 5-minute break, and after that, we'll look at the use of the standalone models that you run from a command prompt. So I'll go through the input, what's the output, and then have a hands-on session in which you can try some calculations and ask us questions as you go. Make some mistakes even and see what happens. It's the best way of learning. So we're going to split the section on the standalone models into three, because there are three models: the seawater model, the composition difference model, and the trace metal model. And the use of the Excel worksheet, we're not going to put that at the end. We'll integrate that into each of these three sections there. And last, after a break, we'll summarize how to use MATLAB and Python functions, and there'll be a demonstration from a computer here to the screen of both of those things, and then you'll be able to try them. And we'll have a session here which you can do whatever calculations you want, try whatever you want, and we're here to help answer your questions. So there are basically two kinds of solutions that the models can do calculations for. And we're just concerned today really with the top box. So it's natural waters containing the ions of seawater or of reference seawater, but not necessarily in seawater stoichiometry. So here are the major ions plus the acid-base species, carbonate, borate, HF a little bit, bisulfate, and so on. There's a bunch of ion pairs here which are calculated by the model, but they're kind of not of direct interest or rarely. And then also these waters of this composition plus trace species, this set of trace metals, and the model will calculate the inorganic complexation of these species. The other models, which you can use with the Python and MATLAB functions, are about the ions of artificial seawater and tris buffers. So that's a bit of a specialized interest, and we won't be covering that today. So these are the properties that the models will calculate. Of most interest to oceanographers, what we call the seawater state parameters, pH on various scales, dissolved inorganic carbon and alkalinity, although they're actually inputs into the model as it is now, and PCO2 and FCO2. And also, the model calculates all of these stoichiometric equilibrium constants for acid-base equilibria, so the two carbonate constants, borate dissociation, bisulfate, ion product of water, and HF, another minority interest there. And of course, it calculates the molalities of the concentrations in two scales and activity coefficients of all species. And for the natural waters containing the trace metals, we get all of the concentrations and activity coefficients, of course, but also the model summarizes the fraction of each metal that's free and the fractions complexed by each inorganic ligand. It makes it easier to deal with the results that way, or to comprehend the results. So focusing on the seawater state parameters, obvious question, we've already got CO2 sys, so why add another model on top of that? So there are two main applications, both, well, the first one particularly obvious. For natural waters with a composition different from normal seawater, the effects of changes of composition on the acid-base chemistry and the seawater state parameters might be significant, and this model is a way of answering the question, are they significant, and what are quantitatively those changes? And also from some of our work, we think brackish waters, those are very slow salinity. We think the model is likely to be more accurate than what you would get from, say, CO2 sys, which is relying on essentially empirical fits to the various equilibrium constants that describe the acid-base equilibria. So just two quick slides to illustrate the basis of of the model. So if we take an example like the dissociation constant of bicarbonate, it and any other dissociation constant depends on the composition of the solution medium. So that means the concentrations of all of the major ions in which the medium in which that reaction takes place. So what we've done in the past is to measure that K2 or other equilibrium constant for every solution composition, i.e. salinity of its seawater and temperature of interest, fit the data set with an equation, and that's what we use, and that's been done for seawater. So the alternative, more general approach is to express the equilibrium constant as a multiple, a product of the thermodynamic value, which only varies with temperature and pressure, and this term in the activity coefficients of the ions. And using MarChemSpec or other models with a similar basis, you can calculate these activity coefficients for essentially any composition, any major ion composition. So why aren't these methods the ones of choice? Well, they're well proven, but they're complicated, and they require large amounts of data themselves, and uncertainties are very hard to estimate. So that's why they haven't sort of taken over the world just yet. So back to the models. What are the ways in which we can use the standalone models? There are basically two. So looking at the model for the ions of seawater, you could enter a composition of the seawater solution effectively, or natural water solution effectively, for a fixed DIC alkalinity and total boron, and then calculate the values of the seawater state parameters and equilibrium constants directly. So your inputs would be most simply temperature and salinity, or temperature and amount contents, moles per kilogram of seawater, or alternatively molality. Or the other use of the model is to calculate the differences, the changes in the values of the seawater state parameters caused by a change in composition, which would typically be from that of a standard seawater composition at some salinity to something a bit different, where some of the ion concentrations are changed. In that case, your inputs would be temperature and moles per kilogram of seawater, most likely. And both these sets of results, these calculations, include estimated uncertainties. Now, in solutions containing all those trace metals, if you just enter temperature and salinity into the appropriate model, the model will calculate the fractional speciation of the trace metals in the seawater, how much is free, how much is bound up with each of the inorganic anions, and output that summary for you. Alternatively, you can enter the temperature in a specific ionic composition and specific concentrations of trace metals, and it'll do the same thing. So a couple of words about concentration units. So the standard in oceanography is moles per kilogram of seawater, for which the IUPAC recommended term is amount content, which isn't very informative. There was an effort in the past to call it molality, rhymes with salinity. I occasionally use this, but you will hear me speak about amount content. And the other unit is moles per kilogram of water solvent, pure water, which is molality. And the reason they crop up, or molality crops up in these models, is all the thermodynamic calculations are done on a molality basis and not moles per kilogram of solution, but the conversion between the scales is straightforward. And if you're interested in activity coefficients and activities in a solution, the outputs of the model, the gamma values, are all molality based, and you should never combine them with an amount content. That would be wrong. And as I say at the bottom, we're not going to talk about artificial seawaters and buffer solutions here. Okay, I think we'll skip this one and move on to limitations. So a very typical use would be to take a solution and equilibrate it to some pair of fixed and known total pH, EIC, alkalinity, PCO2, or fugacity, and this hasn't been implemented fully in the codes yet. Currently, you can fix to DIC and alkalinity and the total boron, fluoride, and if you're interested, phosphate and silicate can be fixed, but we can't do the other pairs. I mean, we're expecting to produce that probably by the end of the year. And in the underlying model, there are some small systematic errors in the prediction of the seawater acid-base equilibria relative to those measured for pure seawater. These are documented quite exhaustively in our papers. And for many applications, I don't think they're going to be important. And they are rather less so. I think they're less significant for cases where you're calculating a change in a property between two media. The systematic errors tend to cancel in that case. Now, our calculation of uncertainties, that also is only approximate, and it's likely to be an overestimate rather than an underestimate if the systematic errors in the model are neglected. And these uncertainties, again, likely to be more accurate in an absolute sense when calculated for a change in a quantity between two compositions. Last, the aims of the sessions. So at the end, I'd like you to be able to do the calculations relevant to you and to understand the output and the results. This is a new model. It's its first sort of public exposure. So your feedback tells us what's needed by the community and what to improve. And bugs and minor issues, we've done what testing we can, but none of us know, we have no single expert in all plans and in all platforms and languages. So if you encounter something that seems a bit weird or you don't understand, please tell us. I can say that we're pretty confident about the underlying thermodynamic calculations because they've been coded in two very, very different solvers entirely independently, and they do give the same results, which is good. So next, we're going to talk about how to use the standalone models that are run from the command line. And these are probably your best option for processing large amounts of data, tens or hundreds of solution compositions or more. And the use of the MATLAB and Python for individual calculations, that's going to be covered a little bit later.